Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so today we're pleased to have Anoop Rao speaking. So Anoop graduated from UT Austin, and then he did a postdoc at the Institute for Advanced Study and the Center for Computational Interactability, and so now he's a professor at UW.
Thanks. Okay, so I'm going to talk today about pseudorandom generators, and this is about conversations that I had with these people, with Mark Braverman, who's at MSR on the other side, Raz and Amir Yehudayoff. So this talk is about derandomization. So broadly, the goal in derandomization is to answer this question: does access to randomness really help in computation? And there are two kind of arenas where you can ask this question concretely. The first is for time-bounded computation. And here the central question is, can you kind of replace every randomized polynomial time algorithm with a deterministic one? Okay. So that's a question you can ask. And the second arena where you can ask this question is for space-bounded computations. So computations that involve a bounded amount of memory. And here the question, or the central question is, can you replace every randomized log space algorithm with a deterministic log space algorithm that does the same task? Okay, and here's the status of what we know so far. In the time-bounded world, we do have some answers that are kind of conditional. Oh, this is cutting off 10% of my slide. This is how to de-randomize time and space-bounded computations. And what we do know is that in the time-bounded world, we know that BPP is equal to P. You can de-randomize every randomized polynomial time computation under some plausible assumption. Okay, and so it's still not a definite yes, but there's some situation generally believed to be true that would imply that this can happen. And in this world, the best in the space-bounded world, the best result to date is as a result of Sachs and Zhu, building on others, that shows that any computation that uses logarithmic space can be and uses random bits can be simulated by a deterministic computation that does the same thing, but uses space that does the same thing deterministically, but uses only space log to the 3/2 n.
What is E on the left-hand side? E is not computed.
E is exponential time, as in like 2 to the or n. Yeah, yeah.
So that's actually a conjecture rather than a class of problems, is it?
Which one?
Yes, if. Is it if a certain conjecture is true, then the answer
This is
yes.
a conjecture.
Yes.
So if
it's not just there's a certain class of problems and a certain class of it's if.
Right. So conjecture is something believable. It says that this class, which is exponential time computations, does not have small circuits. So there's some problem in this class that cannot be computed by a small circuit. That's what you need. And once you have that, then you can get rid of randomness. Okay. But in this talk, we're talking about the second part. This is the world we're going to focus on. And really, we'd like to show, and at least I believe, that it should be true that BPL is equal to L. Okay. Okay. So for the rest of this talk, we're going to focus on a model of computation that's really simple and easy to describe, and here's what it is. And I'll explain why it's relevant to the big problems that I just talked about. The model of computation is called branching programs. So this is a branching program. It's a layered graph where all the edges go from one layer to the next layer. And every vertex in the graph has two edges that come out of it, one labeled 0 and one labeled 1. And here's how you compute with this program. Given a particular kind of n-bit input string, the way you compute using this program is you just take a walk in this graph. So you start at the start vertex, which is colored green at the top, and then you read the first bit, which in this case is 1. That tells you to go to this vertex. Okay, and in this way, the input string just corresponds to a path in this program. And you follow this path, which eventually leads you to the promised land. I mean, the output at the end of the program. Okay, so the output of this program is just the vertex that you reach at the end of this walk.
So do the red and the blue both have to be permutations as you roll them, or could they be actually functions?
That's an important point that we'll get to soon. Okay. So in this case, so in this particular program that I drew out actually computes this function. It computes this sum mod 3. Okay. And more generally, a natural kind of class of functions that these guys can compute is you can compute for any given group, you can compute this group product, right? So given G1 through Gn elements that specify the program, you can compute for an n-bit string the product of the kind of subword that the bit string specifies, and using this program. Okay, but the reason they're really interesting from a complexity theory perspective is that you can reformat every randomized space-bounded computation so it looks like this. Okay, here's how to do every randomized space-bounded computation. You start by using the input to the computation to compute deterministically a width n, length n program. So I didn't say, but the width of the program is kind of the maximum number of vertices in this sense. And the length of the program is this length. The length is always going to be n in this talk. Okay, but every BPL computation can be run like this. You can first use the input to compute a width n, length n program. And then the only step that uses randomness is this step. You then perform a random walk on this program. Okay, so you start at the start vertex and pick an edge completely at random and see where you end up. All right? And if you end up at a designated output vertex, an accept vertex in the final state, then you accept the input. Otherwise, you reject. Okay?
Repeat that? A random walk, just a random string. Random 0, 1.
Yes. Yeah. So use the input here. There are two. This program uses the input first to make the program, to decide what the program is.
The input.
Okay, so we're talking about computation here. So there's this machine is trying to compute some language, decide some language. Okay, so that means that for every input string, it has to decide whether the input string is in the language or not. Okay, and how it's going to do it is like this. It will first use the input string to generate such a program.
What is the property of the program that it generates?
Just that it looks like this.
It could be any program.
Any program. It has width n and length n. You don't know what program it's going to generate. Okay? And once it has this program, it still doesn't know whether it's going to accept its input or not. But what it's going to do is it's going to perform. So that part was deterministic, right? There was no randomness involved. And the second part is the only part where it uses the randomness, and it's going to use the randomness to do a random walk on the program that it generated.
So the magic is in the first step. You're just not telling me.
What do you mean the magic?
It's by definition.
This is what a log space computation is.
Exactly.
Okay? So if you have a machine that uses small memory, then I can always take that machine and turn it into this. Okay, the machine does this. Okay? So the only place where the machine uses randomness, without loss of generality, is in the second step. That's what I'm trying to say. So in general, it's not so clear when you look at a randomized machine what it's doing with the randomness. But here I'm just telling you that you can always force the randomness to be used in this specific way. Okay? Sorry?
But the machine is input dependent.
No, the machine is not input dependent. The program is input dependent.
The program, yeah.
Yeah. So the machine is a Turing machine that has small space.
That particular machine is branching program.
Right. So the Turing machine generates this program, and then the program depends on the input, and then it runs the random walk. So what this means is, if you want to take the randomness out of this process, right? You don't need to actually perform this random walk, right? All you need to do is you need to just estimate what's the probability that a given branching program can output 1. Like what the probability of reaching the output, the accept vertex is. That's really all you need to do. And one way to do it is to perform this random walk. But if you could do it deterministically and in log space, some other way, then you would get rid of the randomness in this computation. Okay, and just to put it in a different way, if you find this way more appealing, you can think of writing out the transition matrix for this random walk. And then all you want to do is you want to compute kind of one of the entries in the nth power of this transition matrix. Okay, so all to de-randomize all of space-bounded computation, all you need to do is be able to kind of compute powers of matrices with small space.
Well, that's assuming all these layers are the same, which they're not in.
No, it's not assuming that all the layers are the same. You can write the transition matrix for the entire graph.
Oh, I see.
Okay, so what I'm going to describe to you now is another way, a path towards trying to get rid of the randomness. Okay, a specific way to estimate this probability of outputting 1. Okay, and that's via what's called a pseudorandom generator. So what's a pseudorandom generator? It's a function that takes a short string, a string of just length t bits, okay, and stretches it out to a long string, a string of length n bits, with the property that if you pick a completely random input and then evaluate this function, then the output of the function is indistinguishable from a uniform string to any program of this type, any branching program of this type. Okay? So what you want is that kind of you feed in uniform bits here and stretch them out using the generator, and then give those to the program. Then you want the distribution. Then you want the distribution of the output of the program in that case to look somewhat close to the distribution that the program would have had if you fed in truly random bits. Okay, so kind of the distribution G of UT is pseudorandom for branching programs. Okay, and the goal is to find such a generator where, first of all, the generator has to be efficiently computable, and t has to be as small as possible, and epsilon has to be as small as possible. Okay. So that's what a pseudorandom generator is. And now let me show you how you can use it to de-randomize programs, to de-randomize small space computations. So remember, this is what every computation does. And all we really need to do is at the end, we need to estimate the probability of outputting a 1 in this program. And if you had a really nice generator, like what we saw before, then the way you could estimate the probability of outputting a 1 here is you could just run over all possible inputs to this generator and see what fraction of those inputs lead the program to get to the accept state. Okay? And because this generator G is supposed to be a pseudorandom generator, the fraction of inputs to this that lead to the accept state is going to be close to the correct fraction, the fraction overall on a uniformly random string that would lead to the accept state. Okay? And this would cost, assuming that the generator was efficiently computable, it would cost only an additional space of t. Okay? So the smaller the t is, the cheaper the step would be. Okay, so that's kind of the connection to de-randomizing space-bounded computation.
Yeah, it would take time 2 to the t.
It would take time 2 to the t, but we're interested in only counting the memory. Okay, so the reason I'm telling you about this strategy is because it's a successful one. An important result is sometime in the early 90s, Nissan showed how to do exactly this, how to get a pseudorandom generator, where the seed length, the amount of bits that you need to feed into the generator, looks like order log squared n. Okay? And that's exactly, and that immediately gives that BPL is contained in L squared.
What do you mean? How? The statement above. the distribution of the random GUT is about the same. What do you mean by that?
It's
What?
P of GUT. So
Yeah.
you run the program.
The two distributions.
Right.
But what does the twiddle mean?
Oh, what distance? I'm talking everywhere. I'm talking about L1 distance.
Okay.
Okay. It's just statistical distance.
So you don't care about the amount of space that G uses?
I do.
Yeah.
I do, and it's small. But for most of the talk, I'll ignore this. Even to find, it turns out that every G that I'm going to discuss is going to be also small space.
So small is T or 2 to the T?
Small is,
So small for you would be like 1/10 would be enough, right? Total variation distance.
yes, 1/10 would be enough in the distance, but small would be, in this case, T. Okay, so what Nissan showed is that you can do exactly this with log squared n bits of seed. So you can take log squared n bits and stretch them out to n bits so that no branching program of width and length n can distinguish that string from a uniformly random string. Okay, and following this, Sachs and Zhu gave what is now the best result for this problem, that BPL is contained in L to the 3/2. But this is not via a new pseudorandom generator, although they did use Nissan's pseudorandom generator as a black box in order to get this result. Okay, and another result, somewhat interesting, is a result of Sachs and Zuckerman that shows that. So remember, so right now we have T's log squared n is the best result for general programs, and if we could make this log squared n log n, then we'd be done. Okay.
So in BPP, right, you have like a constant function of the inputs will give you a false positive and a constant. Like with probability 1/3, you're hitting the ones, and with probability, let's say at least 1/3, you're hitting the zeros. If it should be a 1 or a 0 respectively, right? So can't you just use random walks on expanders to hit a linear sized set out of this usual derandomization trick?
We're trying to get rid of randomness completely, right? So
Right.
I can't do random. I mean, I could just do a random walk on the branching program, and I could estimate the probability of.
But then you would need n.
Right, then I would need n random bits, and you can't de-randomize that because then you have to run over all the n possibilities, to the n possibilities. So the point is, if you use a pseudorandom generator, you can just de-randomize it by doing the naive thing, and it's not so expensive because T is small. Okay. Okay, so one way to prove that BPL is equal to L is to give such a generator with T that's order log n. Okay, and the best generator that we know so far for general programs takes log squared n.
So just one more question.
Mm-hmm.
I mean,
You can ask many more.
again with this expander, I mean, you said that I would need log n bits, but I can just enumerate all
Log
all-
n.
If you have an expander, you need log n, let's say, bits in order to. I'm trying to think of why I can't do a random walk on an expander where these random bits are. I just take logarithmically many, and then I can just brute force enumerate over there.
I didn't understand that idea. So you pick the first vertex and expander completely at random?
Oh, the starting point is what's.
Yeah.
I see. Okay, yeah, that answers my question.
Okay, so that's kind of the state of where we are. And now let me tell you about our results. So first of all, our results are going to be for a somewhat more restricted type of program, but exactly the kind of program that I've been showing you so far. Our results only apply to regular programs. Okay? And what's a regular program? A program is regular if the in degree of every one of these vertices in the middle is exactly 2. Okay? And just to point out, so the types of computation that I talked about with groups, for example, will always produce a regular program like this.
But you're still not making the stronger assumption that both the red and the blue are permutations.
Right. It is weaker than permutation. Right? Because I allow two kind of red edges to come into the same vertex. Okay, and just to point out another side fact, there's a famous result of Barrington that shows that any circuit in NC1 can be simulated by branching programs. Those branching programs are not like these. They allow you to read variables more than once, but they are regular. Okay, so regularity, at least in some contexts, is actually not such a big handicap. Okay, and what we show is that in the case that programs are regular, then we can at least get a good dependence. We can get a really nice generator that has kind of a good dependence on the that interpolates between kind of the result of Saxon-Zuckerman and the result of Nissan. Okay, so let me say what it's saying. So it says that you can get a generator that stretches t bits to n bits, where t is log n times log n plus log d. Okay, where and the output of this generator is pseudorandom for programs where the width of the program is d. Okay. So if you kind of plug d equals n back into this result, then you get something like Nissan's generator, but it shows how to take advantage of kind of the narrowness of the program. And I should have said this before, but before our work, it wasn't clear how to, for example, get a log n length seed even for width 3 programs. Okay, so somehow even a small width, it didn't seem like you could take advantage of that, and we show how to take advantage of this.
Oh, so you do slightly worse than the width 2 result?
Yes.
You get log n log n.
Yes.
For constant width.
Yes. So the width 2, right? Yeah. So for width 2, the result was just exactly order log n, and we have an extra log n. Okay, but what I'm hoping is hiding in here is a technique that will be really useful, and that's what I want to get at more than this result itself. And okay, so let me start talking about how we prove this. So it turns out that we're not really going to design a new pseudorandom generator. We're just going to take the old pseudorandom generator, in fact, something that's very similar to Nissan's pseudorandom generator, and just give a better analysis of it. Okay. So let me start first by describing the intuition for Nissan's pseudorandom generator. And this is not exactly how Nissan presented it. It's an intuition that's developed, a way of presenting it that's been developed over several works. Here's the basic idea. So let's forget about trying to construct a generator from scratch. Let's assume that somebody shows up and tells you, here's a generator to generate n over 2 bits that are pseudorandom. Okay. Suppose there is a function g that can take t bits and stretch those t bits to n over 2 bits that are delta pseudorandom. Okay. So now the question is, suppose you actually want a distribution on n bit strings that's pseudorandom. So how can you take this generator, which only generates n over 2 bits, and make it generate, and use it to generate n bit strings? It's a question for you. What's the first thing you would try? Right, exactly. So just use the generator twice, right? So you can just use 2 independent seeds, stretch the first seed to n over 2 bits, and then the second seed to n over 2 bits, and just put them together. So what happens when you do this? You get a new generator now. Its seed length is doubled. It's become 2t. And its output length has doubled. And also its error has doubled, right? So what you get is that after you do the walk up to this point, the distribution on the vertices on this middle layer is going to be delta close to the correct distribution. And then you do another pseudorandom walk, which will leave you at a distribution on the final output that's now 2 delta close to the correct distribution. Okay, so that's what happens. So the main thing we're going to try and do is try and de-randomize this step in some sense. So this is way too expensive. We can't afford to spend 2 seeds to double the output length of the generator. So we're going to do something more clever. Okay?
You're fine with the doubling of the error.
The doubling of the error we'll not be able to save, these people were not able to save. But then later I will show you that we save on it. Okay? So now I'm going to show you how to save on the doubling of the seed, which is what Nissan and this line of work managed to do. But they didn't manage to stop the doubling of the error, which is what leads them to get worse results in this context. Okay? So the main technical tool that's useful to kind of avoid doubling the seed length is what's called a randomness extractor. Okay, so I'm going to be a bit informal here in describing what it is, because it's not so important for this talk. But what it is a way to kind of start with a distribution that is not close to uniform and make it uniform. Okay, so it's a function that takes 2 inputs, a t-bit string and a string with k plus log 1 over epsilon bits. Okay, and what it outputs again is a t-bit string. And the property that it has is that if the input distribution has entropy that's at least t minus k, okay, so entropy is k bits less than full, then the output of the extractor is epsilon close to uniform. Okay, so what the extractor does is it kind of takes these additional k plus log 1 over epsilon bits in y and kind of reloads that randomness back into the x that you started out with.
So y is assumed random decision.
Y is truly random. Okay, so x is an arbitrary distribution that has entropy t minus k, and y is an independent string of random bits. And what the extractor can do is take this independent randomness and kind of refill the randomness into x.
Do you need to make some kind of assumption like no particular x is too likely? Or?
Right, so it turns out that, so I wrote here kind of Shannon entropy, but in reality to make all of this possible, you need to measure entropy in terms of min entropy. The min entropy of distribution is k if the weight of the heaviest string in that distribution is at most 2 to the minus k. Okay, that's an even stronger measure of entropy. But in this talk, I don't want to make distinctions between these kinds of things. Okay, so I just want to leave it at the. Let's just believe for a second that as long as the Shannon entropy is t minus k, then this extractor works. Okay, and there are technical issues that come up from the fact that you have to actually deal with this measure of entropy, but let's not deal with them here.
I'm a little confused whether we should think of big X as a fixed string or a distribution over strings.
Big X is a distribution on strings.
It is, okay.
Okay, so it's a distribution on strings that has entropy t minus k.
Okay.
So it's not quite uniform, but you would like to get from it a uniform string of length t. Okay, and there's no way to do that deterministically. You have to throw in more randomness because the entropy is only t minus k. Okay, and it says what it says is that if you do have an extra k bits of entropy, you can add that back. Okay, so that's what an extractor is. And so now here's a more clever way to kind of double the output length of a pseudorandom generator. Okay, what you can do is before we just ran the old generator twice on 2 independent inputs. Okay, now what we're going to do is we'll run the first generator to generate the first n over 2 bits. But for the second n over 2 bits, we're not going to spend another t bits of seed. Okay? What we're going to try and do is just reload the entropy that x lost. Okay? So we're just going to use a small string y and extract reload the entropy back into X, and use that as the seed for the second part. Okay.
So you say reload because knowing Gx reveals some information about X?
Right. At this point, the program has remembered some information about X. Right. The intuition is that at this point the program has remembered some information, but hopefully not a lot of information. Right. It only has so many states to remember information about X. So even if you condition on the vertex that you're at in the middle part of the program, you expect X to still have a lot of entropy. And that's what you want to take advantage of. Okay, so just to maybe I shouldn't try to do this, but so here's a statement about extractors that's not true, but it's almost true, that I want you to believe for the rest of this talk. The statement is that here's another way to view what an extractor is doing. Suppose you have correlated random variables x and a with the property that x is uniformly distributed and a is distributed on k-bit strings. Okay, then what the extractor does for you is the extractor has a property that if you look at the joint distribution of a and the output of the extractor, then this is epsilon close in statistical distance to the distribution of a and an independent uniformly random string. Okay? And again, the intuition is typically fixing this k-bit string will reduce the entropy of x by roughly k bits, and then the output of the extractor should be uniform for every fix.
So how far from being true is this?
Well, so to make it real, the problem is there could be some fixings of k-bit strings that actually completely annihilate the entropy in x, but these fixings are unlikely. So you have to do this kind of argument. Yeah, so you have to. It's not very far from not being true. But I don't know how to measure this distance. Okay, so once you have this view, here's how you analyze this construction, or here's the intuition for it. Let's look at the path that's defined by this supposedly pseudo-random sequence of inputs. And let's look at the vertex that's crossed by this path in this layer A. Okay. Then what you have is that from what I said before, the vertex A has only kind of log d bits of information about x. Okay. So if you set y to be something like log d over epsilon, then the joint distribution of A and the seed for the second part is epsilon close to the distribution of A and completely independent bits. Okay? And so what this gives you is you get a new generator where now the seed length, instead of being 2t, is t plus something that's logarithmic in the width and epsilon. Okay, and we double the output length just like before. And in order to make everything work, we had to pay a small price. We had to add this error of epsilon to the error of the pseudorandom generator. Okay, because the output of this extractor is not exactly uniform, but just epsilon close to uniform. Okay. So that's kind of the main idea in the work of Nissan and all these works, or one of the central ideas, is that you can kind of do this doubling more efficiently than the naive way. Okay, so once you have this, you can then start making a pseudorandom generator from scratch. Okay, how would you do it? Well, let's start with just a trivial generator. So let's take the generator that takes log d over epsilon bits of seed and just outputs one bit. Okay, just outputs the first bit of the seed. Okay, so this is kind of a lossy generator, but it actually it works, right? The output is completely uniform, so no program can tell that apart. And then we'll just keep doubling the output length of this generator using the ideas that we saw. Okay, so in the ith step, we'll kind of add another log d over epsilon bits of seed, and we'll double the the output length of the previous generator.
Don't you collect log n epsilon error?
Right, we'll see. Yeah, we will. We'll collect n epsilon error. We'll see what happens to that. Okay, so what happens to the error? The error of the first step is 0. And in each step, the error that you get is epsilon plus double the error of the previous step. Okay? And if you do this, after you reached log n steps of doubling, you're now generating n bits that are pseudorandom. Your seed length is now log n times log d over epsilon. And the error has become, in every step, kind of the error doubles. And there's log n levels of doubling. So what happens to the error is it becomes something like n times epsilon. Okay? So that's the construction. So there are two reasons why the seed length for Nissan's generator is log squared n. The first is that d is n, right? So this term is always log n times log n, if you want to handle with n. But even if you wanted to handle with 3, to get a meaningful result here, you need epsilon to be smaller than 1 over n. Right? So this term is always going to be log n, either way. Okay, so that's why the seed length is log squared n. And what we're going to do is we're going to show how to analyze the same construction, but not pay so much in the error. Okay, not add the error like this. Okay, so let me just give you some intuition for why that should be possible. Okay, let's look at a couple of special cases. Okay, so intuitively, so I'm just going to make some vague statements. The program only has kind of log d things about the input, that log d bits that it's remembering about this huge input, right? So it shouldn't be able to pay attention to all parts of the input. So any fixed program should be, in some sense, paying attention to only some parts of the program, right? Some parts of the input. Most of the input it should be just kind of ignoring, and that's what we want to take advantage of. Okay, so let me give you an example. Let's say, for example, that the output of the program is completely independent of the first half of the input bits. Okay, so let's look at the middle layer and let's label every vertex there by the probability of reaching the accept state with a random walk starting at that vertex. So let's say, for example, that you're in the situation that if you start from here and you take a random walk, you reach the accept state with probability 1/3, and it's the same for every vertex in the middle layer. So what does this mean? It means that it doesn't really matter what happened here, right? Once you get to here in the random walk, it doesn't matter which vertex you're at. You're still going to hit accept with the same probability, right? The settings of the bits here didn't matter. Now, in this case, if you wanted to analyze this construction, you see that the error from this side of the program is irrelevant, right? It doesn't matter how far away you are on the distribution at this layer, because every one of those layers is supposed to accept the rest of the input with probability 1/3. Okay. So in fact, if you knew the program looked like this, you would prove that the new generator that you get by combining these two is not 2 delta plus epsilon pseudorandom, but just delta plus epsilon pseudorandom. You would just have the error from the second part of the construction.
So you aim to take epsilon 1 over log n?
Eventually, yes. Eventually, we're going to take epsilon to be like 1 over log n. Okay, so this program completely ignores the first part of the input, so we shouldn't consider that part when we add the error. And another example, so here's a program that completely ignores the second part of the input. So the way I've captured that is by labeling the acceptance probabilities in the middle, and you see that they're all either 1 or 0. Which means that once you hit this vertex, then no matter what happens, you're going to accept. And once you hit this vertex, then no matter what happens, you're going to reject. Okay, so again, it's irrelevant what the bits on this side of the program are. Okay, and this time, if you try to do the analysis in a smart way, it doesn't matter what happens here, right? The only thing that's relevant to fooling this program is whether you could fool it up to this point. Okay, so if you did this doubling, you should only count a delta. The output of the final generator is delta pseudorandom instead of 2 delta plus epsilon pseudorandom. Okay, so the reason I'm showing you these cases is because what I'm going to argue is that every program, in fact, is some kind of combination of these kinds of things. Okay, so in fact, so here's what I want to do. I'm first going to describe a way to measure the information in different parts of the program. Measure the amount of information that different parts of the program are gathering. So let's say you have a particular layer of the program, like this. Let's label every vertex in the program, just like on the previous slides, with the probability that you will accept a random string starting at that vertex. So the probability that a random walk starting at this vertex hits the accept state. Okay, so that's what those labels are. And let's label every edge, let's weight every edge with the difference of the labels of the 2 vertices that it connects. Okay? So this gives some weight on the edges. And now let's look at what happens to our examples. So in this example, what can I say about the weight of all the edges on the left? It's 0, right? All of these edges have 0 weight, right? Because all of these probabilities are 1/3. Okay? And the same thing happens in the other example. In this example, all the edge weights here on this side are 0. Okay? And in general, what we're going to do is for any program or any segment of a program, let's define this measure W of the program to be just the weight of all the edges that are in the program. Okay? So in general, I'm given a segment of the program. So there's some numbers A, B, and C, which are supposed to be acceptance probabilities at the end of the program.
These weights can also be negative.
No. I'm taking the absolute value of the differences. Okay? So I'm taking the absolute value of the differences in the acceptance probabilities. Okay, so they're always positive. So that I claim is a good measure of how much information this program is storing about its input. And so here's how our proof is going to go. So remember, I'm going to try and analyze the same generator as before. Right? So the generator starts with the single level, and each time you double the output length. We're going to prove 2 statements. First of all, we'll prove that if you look at the error of the ith generator, okay, and what I wrote here is kind of the expected value of the label you get to when you feed in pseudorandom bits versus truly uniform bits, the difference in the expected value. Then this can be bounded in terms of the weight of the program times I, the level of the generator, times epsilon. Okay, so if the weight of the program is small, this error is actually really small. Okay, and the second thing we're going to show is that in the case, so this statement has nothing to do with the regularity. Right? It applies to all branching programs. And the only place where we use regularity is in the second statement, where we show that if the program is regular, then the total weight of all edges in it is completely independent of its length. Okay? It only depends on the width of the program. Okay, the weight of all edges is at most 2D if the width of the program is D. Okay, those are the 2 theorems that we'll prove. And those 2 turn out to be enough. So if you plug everything back in with those statements, you get the final error of the generator is actually only epsilon times 2D times log n, instead of epsilon times n that we had before. And this allows you to get our stronger results. Okay, so let me next talk about maybe the most interesting part of our work is analyzing this measure of information. Okay, so that's what we want to prove. We want to prove that if a program is regular, then the total weight of all the edges is at most 2D. It's independent of the length of the program. Okay, and to understand this, I'm going to talk about a pebble game. Okay, a certain kind of game. So let me show you what it is. Let's imagine you start with k pebbles placed on the real interval from 0 to 1. Okay, so here are the pebbles. What I allow you to do in this game is at every step, I'll allow you to pick any two of the pebbles, say those two, and move them towards each other. Okay. So there are k pebbles on the line. You can pick any two pebbles and move them towards each other. And if you move them towards each other with a distance of alpha, then I'll say that so far you've made a gain of 2 times alpha. So you've translated the pebbles by a total of 2 alpha. Okay? And then you can continue in this way. So you can pick another 2 pebbles, move them towards each other by a different distance, and I will measure how much you move them together and add that to your total gain. Okay, so this is a particular kind of process involving pebbles. You know how it took me a long time to make this animation, so I have to like dwell on the slide just to make myself feel like I didn't waste my time. Okay, we can do it again. All right, that's a pebble game. Now you might be wondering, what does this have to do with pseudorandom generators, branching programs, or computer science? But here's what it has to do. Suppose you told me that you had a regular program, then I claim that program specifies a way to move pebbles around. Okay? So say you gave me this program, and it has this layer of vertices with those numbers on it. Then what I can do is I can put 2 pebbles on every vertex at the end here. Okay, and 2 pebbles here on the number A. And two pebbles for each of the numbers, as you can see. Okay, and now this program specifies a way to move these pebbles exactly in the way that I talked about. Okay, so you can let's first move the 2 pebbles that correspond to the 2 edges connecting to the top vertex there. So you can pick 2 of the pebbles from these 2 vertices and move them to the next layer in the program. And then what you're doing exactly is picking 2 pebbles, in this case B and C, and moving them towards to the midpoint of B and C. Okay? And you can do this for all the pebbles. Right? So for every edge, you can move a pebble along it. And you now end up with the same kind of configuration in the next layer. Okay, and what's the point? What is the total gain that we did in this pebble game? What does it correspond to in terms of the program? It corresponds exactly to the weight of the edges, right? The weight of the edges in this layer is exactly the total gain that we experience in this movement of pebbles. Okay, so all we need to do now to prove this theorem is we need to prove, and this is the only place where we use regularity, right? So for all that to work, I put 2 pebbles on each vertex, and it was really important that the number of edges coming in is equal to the number of edges going out.
So is this false if you just assume bounded degree?
Bounded degree, yes, it's false. Well, I mean, you can always assume bounded degree because the width is bounded. So if the width is 3, the degree is at most 6. But yeah, it's actually false, and we have it can depend on n, even with width 3, and unbound, non-regularity. Okay, but okay, so now we've just reduced to the following situation. We just have a bunch of pebbles on the line, And we want to know, what's the maximum possible gain you can get using a pebble game on these pebbles. Any guesses? No. It's actually, I think that 2D is actually wrong for these general positions. Anyway, so it turns out the bound we can prove is that the total gain is always just exactly the sum of the pairwise distances between the pebbles. Okay?
So this is the sort of slowest possible pebble game you're talking about, right? Like the one
this is the one that causes the pebbles to move the most.
Yeah. Okay.
Right? Eventually, the game ends when all the pebbles are in the same place.
But so this
right?
is relaxed from what we actually look at, right? Because in the branching program, we're going to have them always move through.
Right. That's true. That's true. But actually, it's even tight in that sense.
Okay.
So you can make a branching program that realizes this bound.
Yeah.
Okay. Okay. So I claim that the total game is just the sum of the pairwise distances between the pebbles. And to see this, it's not hard. What I'll actually argue is that in each step, when you move AI and AJ towards each other for a gain of alpha, that you have to reduce this quantity by at least alpha. Okay? And that would prove it, right? Because this quantity is always non-negative. And if every time you have a gain of alpha, you reduce it by alpha, then you can't have a gain of more than this quantity. Okay, and it's actually really easy to see. First of all, when you move AI and AJ towards each other by alpha, then the term AI minus AJ reduces by alpha. And what happens to the other terms? If you have a pebble that's not in between AI and AJ, right? Then when you contract AI and AJ, one of the pebbles is moving away from this outside pebble, and one of the pebbles is moving towards this outside pebble. So all of those terms remain the same, right? On the other hand, if you have a third pebble that's in between AI and AJ, then when you push AI and AJ together, it only shrinks this quantity even more. Okay, so overall, that's an upper bound on the total gain that you can get in this pebble game. Okay, which means that if you start with the branching program, and you have two pebbles at 1, the accept vertex, and all the other pebbles are at 0, then you get a bound of 2D. Okay.
So is it maybe true that the gain is always the same no matter what order you do things?
No, that's not true, right? It's because of what I described. So if you have pebbles in between two pebbles, then you can reduce this quantity much faster.
Yes, I'm not saying it's equal to that, but I'm asking if you're given the AIs.
Okay, so let me finish what I was saying. So on the other hand, if you always choose pebbles to move which don't have pebbles between each other, then it's tight. So you can always achieve this bound by picking pebbles that don't have anything in between them. So it can be different. Okay, so that proves the bound on the total weight of all edges in the program. And the second part is not very complicated. It's just a calculation, but the basic thing to note is that the point of measuring the weight is that if you know that a program has small weight, then if you feed in two distributions A and B which are epsilon close to each other, the expected value that the program can have on the final vertex when it reads these inputs can disagree by at most the weight of the program times epsilon. If you think about it, it's not hard at all. So if you think about a single step, if the weight of a single step is only 0.05, then even in the worst case, if you have completely different inputs, you'll end up at a value that's only apart by the sum of the edges. Okay, so if you're epsilon close, you'll just be epsilon times the total weight of all the edges in the program. Okay, and this is enough to give the results. So I wrote the analysis here, but it's not really so hard. So you just argue about, so now we're again arguing about doubling the output length of the generator. And you can bound the error in terms of kind of using induction in terms of the weight of the left part of the program and the weight of the right part of the program. And these two weights add up to give you the weight of the entire program. Okay. So it turns out you can bound this. I think I'll skip the technicalities, but you can bound it to give exactly the bound that I talked about. Okay, so that's it. That's our result. It's a generator for regular programs that uses seed length log n times log n plus log d, if the width is d. And there's some interesting open problems. Obvious ones: get rid of all the caveats. Get rid of the fact that it's a regular program. And here you can't use this measure of information that I talked about. You have to use something else if you want to really get a win, and we don't know exactly what that something else is. Right, there's a log n, which I think is coming from the fact that it's this construction. I think the construction inherently has this log n, but I'm not sure. And I think the most interesting thing about our work is this measure of information on the program, and I wonder if there are other measures of information. Does that make sense? Thanks.
That picture.
It's supposed to be coffee, but it's very black coffee, apparently.
Cool.
Thank you.
Thanks again.